All right. Good afternoon, everyone. So we'll get started. Um, so quick announcement. Pretty much everyone voted, I think, except for one person. So we're going to be having our final on Thursday next week.
Oh my God.
Yes.
Well,
It was, it was far enough that even this one person wouldn't make the difference. So we're going to do it on Thursday. Yeah, and so on finals week, you guys won't need to come in, which I guess is one positive. I guess any questions about final or anything else before we get started? Nope. Okay, so we're going to pick up where we left off last time. Remember, the lecture is focused on DERs, distributed energy resources, and we, I believe, kind of finished up by talking about the interconnection processes. So, one thing that I kind of wanted to mention, so we were talking a little bit about these smart inverters that provide voltage control and VAR control. So just a little bit more details about this. This is kind of the, I don't want to say odd man out in terms of DERs, right? But they do maybe work a little bit differently. We think of this as more of support for DER as opposed to necessarily being what we traditionally think of as like flexible loads or distributed generation. So one of the things, right, that we've talked about with things like rooftop solar that inject power back onto the grid is that you might have some voltage issues, right? And so these inverters are designed to help mitigate some of that. They adjust reactive output, reactive power output based on the voltage at the point at which you're interconnecting your DER. So a lot of that backflow issue that can get voltages higher than allowable, this can help reduce that. It can also help maintain voltages within certain limits. Yeah, and so we're not going to get into the kind of physics of how this works. Just know that there are smart inverter technologies that essentially help support DER generation at the point of the end consumer. Okay, so one of the things that we have been alluding to is the ability to have flexible loads, right? And so there is this subset of distributed energy resources that's actually generating electricity and reducing loads. But then we've also talked about things like smart chargers or smart thermostats and other items which are considered distributed energy resources. And the way that it works is essentially by taking some kind of load, so the typical load that you might see over a period of a day, and then moving it, right? And so this might be like, instead of charging your car right when you get home, you plug it in and you have a device that says, oh, let's think about charging at a later time because it's cheaper, right? Or you and a group of houses in your neighborhood all have smart thermostats. Maybe the load is really high, and so it'll say, or it anticipates load to be really high at the peak part of the day, so it says, oh, we're going to run your AC earlier than you would normally to like pre-cool your house. And so the mechanism of load shifting, there's a couple terms that you might hear. So peak shaving is one type of load shift where when your load is at a peak, Instead, if you're moving that load around, you shape the peak, and so you go from this red line, which has a much sharper rise, and essentially move that load elsewhere so that it drops down, and you stress the system less. So generically speaking, we call that peak shaping. And then in a sort of corresponding way, and oftentimes this is, these are sort of complementary with each other. You have valley filling, and so in troughs of your load shape, or when your loads are generally sort of lower, right, this is where you can fill in that load to other times. And then we call load shifting from like one point to another. So this is a graphic that roughly kind of shows visually what these sort of load shift terms look like. Any questions about this? The purpose of the load flexibility might be serving different things, right? You can imagine that maybe peak shaving may have to do with like reserve capacity. Maybe the valley filling helps to deal with like ramping issues. Maybe load shifting might have to deal with like curtailment, right? And so there are different mechanisms that provide different services to the grid. And so each of these may correspond to different services that the grid can use. So examples of these technologies that I was mentioning: smart thermostats, managed EV charging, also smart water heaters, right? And so this will heat the water at different times, thinking both about your demand, but also the ways that it can provide services to the grid. Example on campus, I don't know if we actually talked about the chiller at all, but this is a way that you can change the timing for sort of employing this chiller to move cool air for campus buildings. I don't know if you want to say anything about the chiller, but yeah.
Sure, yeah. We have 8 chillers. Each thing uses about a megawatt of electricity. They make cold water that cools most of central campus. And we also have a 5 million gallon tank that you can fill with water. Well, it's full of water, but it depends on the temperature of the water. So you can use the chillers to make cold water and store the cold water, and use the cold water when you want to. So it's essentially like a thermal battery. So.
And as I understand, it was recently, ish, I guess years ago at this point, sort of optimized to think about like energy prices, right? And that was work that was done by so I'm thinking of Devin. I know that she wasn't the primary person. There was like a chemical engineer PhD student. Is that right?
Yes, Gustavo.
Yeah, and then Devin was a master's student one of the first master's student in the EGG program, and she had helped on that chiller project.
But when I got here, they said that the price was flat.
The
price was flat, and Devin and I went and met with WAPA numerous times.
Yes.
In Folsom.
And found out that wasn't the case.
To understand what was going on.
Yeah.
Basically, eventually realized that our load was fully subject to wholesale market pricing, and there was flat components like hedging, and hydro was flat, but regardless, we always were scheduled in the wholesale market for our full load.
Yeah.
And there was questions about whether that was how that was allocated, because we're part of a pool, and so like for a given hour of shifting, were we getting the full benefit or cost of that hour?
Mm-hmm.
And the answer was yes, but we had to really peel the onion to get to that.
Yeah.
Yeah, but then the algorithm was created by the grad student in chemical engineering, but Devin did help with some of the coding and I believe constraints, as well as
Yep.
building like screens that the operators use to know what they ought to do at a given time.
Yeah. So when we think about kind of the load flexibility here, the chiller was designed, one of the constraints that was introduced, or I guess probably not even the constraint, the objective function was to be responsive to like prices, right? And do you know how much money they saved, or you guys saved with that algorithm?
We estimate 100, well, so the equipment costs probably 2 or 3 million a year to run, and we estimate that just the basic load shifting day by day saved about 150,000 a year, and then currently with demand response programs, we're also making about 350 a year.
Yeah. So, 2 students saving the university $150,000 a year, pretty good deal.
And making 350. So that
Yeah,
that's
with
the
the
net
yeah.
benefit is more like 500.
Yeah. Okay. So $500,000.
Yeah. As long as DSGS stays funded.
Right.
But we'll see about that.
Right. Okay. So, what is we're talking about all of these DERs, and this is like technology that's been coming or been around for a while, newer stuff generally, and so there are other ways to deal with some of the problems that we were talking about on the grid, right? Like with peaking, valley filling. You could get more generators that could ramp. You could have more capacity, and so when we think about sort of the options to provide services to the grid, DERs are considered under this category of options that we sort of call these non-wires alternatives, NWAs. And these alternatives are pretty compelling, right? Because you may sort of offset the need for some of these other infrastructure upgrades that I was just mentioning. And so the use cases of these can be tremendously cost effective relative to what a utility might do traditionally, right? So I may be able to defer transformer or substation upgrades. I can reduce peak loads on congested feeders, meet reliability criteria without having to put in new equipment. And then I can even target DER deployment, right, in places that have stronger constraints. And so there is this sort of constant, there's this sort of struggle with both utilities and PUC as we think about these types of options, because right, some of these benefits are pretty compelling, especially on the cost front. On the other hand, it requires some level of sort of accountability and trust, right? And so this idea that traditionally you introduce some kind of projected load into like a neighborhood, and the utility has like a specific equation, an algorithm of like when I need to install the substation. So I guess what I'm getting at is, can the PUC trust that if you implement a smart charging program for a bunch of like EVs, are they going to follow that? Or, what if someone decides not to do that and then they blow out a transformer, right? That's kind of stressed out. And so the PUC and the utilities kind of continue to navigate this balance between, how much we believe we can get out of, these DER services, and trust in the way that they will work, in order to reap these benefits, or do we need to be sort of overly cautious and not necessarily partake into these benefits because we don't trust in the ability of these flexible load services to provide what they're actually promising, right? So that's a sort of constant navigation that continues to happen. Yeah.
So, weren't all the previous technologies new equipment? Like, I know they're not additions to like the distribution or transmission network, but.
Mm-hmm. So, I'll give maybe a really kind of simple example. Let's say your transformer is like close to getting, a local neighborhood transformer is close to being overloaded, and then someone in that neighborhood decides to buy an electric vehicle, right? And if they would just charge their EV when they get home, let's say that puts you over the sort of thermal threshold for the transformer. So traditionally what the utility does is they say, they'll look at the load that's getting added into the neighborhood when you request, let's say, that this would get triggered by, you know, an electrician going in to install a charger. And maybe by the utility's equation, they're like, okay, we gotta put in a new transformer, and that's gonna cost all this extra money, right? So the alternative is, okay, that person installs the charger but says, oh, I'm going to participate in some kind of smart charging program where I'm only going to charge the car at times where that transformer isn't heavily loaded, and therefore the utility doesn't have to go in and install that equipment. Does that make sense?
Yeah, I was caught up in like the technicality of what is considered equipment.
Yeah.
But I think I understand.
Yeah, I guess I'm referring to like the traditional grid infrastructure, like wires and poles and transformers and that sort of thing, versus the actual like DER equipment. Yeah.
I saw in seminar last quarter.
Yep.
Presentation showing benefits for DERs. Have there been any real rollouts in controlled bay?
Oh yeah, yeah.
PV territory?
Oh, absolutely. There's plenty of DER programs that exist. Are we going to talk about any of
I'd
them?
be curious, like, could they throw in some sensors into like the local, you know, the area, and so they can have like some kind of basis for trust or not trusting, you know?
It depends to what sorts of grid services that you're providing, right? And so, in some cases, you don't need like local sensors. That would be more if you were targeting benefits to like that particular set of equipment, like at the distribution level. But you can imagine just on a really hot day where your load approaches your capacity reserves. You know, there is a utility program that controls the smart thermostats, and so they'll just turn off a bunch of AC units, right? And that doesn't require telemetry at the sort of distribution level. We just need to know the relative relative load versus capacity in the aggregate.
Okay.
Yeah.
I was thinking distribution level where there's usually not as much.
Yeah, at the distribution level, it's trickier. There are a couple pilot programs that are looking at at certain things at the distribution level. But yeah, I think fundamentally it's just harder to do at that level. I think most of these programs are thinking more about at the like wholesale level, usually, not always.
Sure,
But,
I mean,
yeah.
I appreciate it. I think they can make it make sense.
Yeah, although, you know, I would argue that that a substantial amount of the value is probably at the local level. It's just harder to realize that.
Yeah, if they're gonna truly give credit where credit is due, yeah, they gotta explore that.
Yeah. Did someone have a comment question? Okay. Yeah, so there are additional benefits also to resilience that people often think about. So with PV storage, microgrids, so grid tide mode, you can have service maintained during shorter sort of disturbances. And then kind of coupled with that is this idea of islanding. You can set up a sort of local islanded grid that maintains power for critical elements. So think about things like hospitals, fire stations, that sort of thing. And don't necessarily kind of discount the value that people put into these things. You'd be kind of surprised. There's some recent literature about, if you invested in like a storage device, right, and you're thinking about this from just an economic opportunity to like arbitrage power, the value of doing that is actually pretty low relative to the cost of the storage, right? But actually, the reason why people do it is that arbitrage is oftentimes a secondary, like ancillary value, and the primary one being sort of back up in the case of blackouts. And people put, I'm not gonna call it uneconomical, right? Because we put different utility into how much we value having power, right? But when you look at the relative value of what they're spending to have backup in cases of blackouts, it's actually a tremendous amount of money, right? And so it means that people value that backup service quite a lot. And so the value of resilience to some set of people in the population is very, very high. There are also sort of wider system benefits besides just being able to have this sort of like islanding capability. You can accelerate restoration after an outage. It can reduce reliance on other forms of resilience that are, let's say, dirtier, right? So diesel backup generators. And it can help to enhance wildfire mitigation strategies. So we talked about public safety power shutoffs. In the events of like high wind, you may be able to still maintain generation in the case that these things are happening. Yeah.
Can I try to echo back what islanding means so I can see if I understand it?
Sure.
So if an area of the grid is islanded, that means that it can survive disconnected from the rest of the grid for some short amount of time.
Yeah, so imagine that you have some kind of backup power. So let's say it's like rooftop solar or even a diesel sort of generator. The way that the grid is hooked up, and if you were to just generate power locally, because you're still tied into the rest of the grid, it's not going to work very well to like power your home. You have to actually disconnect the sort of circuitry, and so there's some hardware requirements that let you do the
It's
islanding.
still connected. I guess you're still powering the rest of the grid.
Yeah.
Turn off the main.
Yeah, and so you want to have something to basically disconnect and allow you to power just a small portion.
Okay.
I guess just to reiterate, it's very true. Like when I got my solar system installed, I was like, "Are you trying to like be able to island, or what's your motivation here?"
Yeah.
It's like, if
Some people are motivated to do that. We call that what is the term? Grid defection. And so people like, oh, I hate my utility. Well, I mean, maybe that's reasonable. You know, they hate their utility and they're like, I don't want to have anything to do with it. You can do that. You can grid defect. You can put up solar, have local storage, disconnect from the grid. there have been a couple studies that have looked at the like cost of doing this, and it's very expensive to totally be able to, you know, run a system like that.
And I'll tell you, like 3 years ago, we had a local outage. Like my youngest son was like in a month old,
Mm-hmm.
and a tree fell on the lines, and so we were without power for like 3 days in the winter.
Yeah.
And, I would have loved to have something to keep the house warm.
Yeah, and you'd probably be willing to pay a lot of money, a lot more than, you know, your expensive electricity rates, right? On the margin for what the utility is provided from electricity when you really need it, it's probably a lot higher than what the actual price of electricity
Dad,
is. Yeah.
you know, having the ability to keep my house warm, it was like, yeah, felt like I failed as a father.
I left them in the spirit, yeah.
Okay. Equity opportunities through targeted DER deployment. So we've talked about this as a theme in other portions of the class. So a lot of the adoption of DER technologies and services are historically sort of concentrated in higher income households. And so we think about the benefits of these things occurring sort of unevenly across the population unless you have some kind of intervention. Yeah, so rate structures that subsidize early adopters can shift costs towards non-adopters. Does anyone recall a pretty substantial example of this?
Never.
Yeah, so the net energy metering, the way that it was designed, ended up shifting a lot of those volumetric costs that pay for fixed infrastructure to population of people who don't own rooftop solar, right? And so this is an important example of why this matters. So there have been a number of strategies that are specifically oriented towards providing certain populations resources to use and get things like solar and storage, right? So there's specific programs that do this and provide funding and subsidies. Community solar and storage, microgrid serving specific populations. Yes, and targeted, okay. I'm totally blanking on this.
Non-wire alternatives.
Yeah, non-wire alternatives in disadvantaged communities. So all of the, various DER services and technologies.
We're applying for an S2.
Oh yeah? Okay.
2, actually.
Yeah, nice. Like the campus? But that's not in the sort of equity portion of SGIP, I would assume.
I think the battery we're trying to get is equity S2.
Oh, okay.
I think that we have low-income parcels in the vicinity associated with students. I don't exactly know why we. I think we're gonna get it.
Okay, yeah. Yeah, interesting.
It's gonna be like a 750 kW 4-hour battery.
Yeah. This is not a slide you guys have to memorize or anything, just kind of leaving this here as a reference table. Yeah, if anyone's interested in learning more about some of the specific programs in California, here's a list of, a couple of the sort of larger ones. I'm not going to go through these, but if anyone's interested, we'll leave that as a resource. Okay, So we've kind of talked broadly about DERs, and I want to focus on the most kind of substantial DER technology, which is behind the meter storage, or sorry, solar, not storage. Okay, so hopefully we're all relatively familiar with what this is at this point, right? So PV installed on customer premises, and then interconnected at distribution voltages, right? So not utility scale. This is all the stuff that's like locally installed. Doesn't go through the transmission system to provide electricity. It's starts at the distribution voltage. And is usually servicing within that sort of distribution network. Some of it could get exported to the grid, but meant to sort of offset local load first. Yes?
So just check my understanding of like behind the meter solar. If the PV system is at the time only serving the load of the house, it is not increasing the voltage of the distribution network, right?
Yeah, that's right.
Okay, but when it exceeds that, that's when the network gets a little extra loaded.
If your batteries are full.
Okay.
Yeah.
If you're exporting it to the grid, basically.
Yes, exactly. Yeah, so again, kind of the motivation behind focusing on this, it's by far the largest category of DER technologies. You got over 1.5 million behind the meter solar systems installed in California. This is kind of a breakdown. It's a little bit older of a chart, but these are monthly installations of rooftop solar in the major IOU territories in California. And that has gone up even higher in recent times. Until 21? Until NEM 3. So installed capacity doubled, has nearly doubled since 2020, but then fell off quite sharply following the NEM 3.0 implementation. Okay, so characteristics of behind the meter solar, they can still vary quite a bit in size, right? So we think about residential systems that can be anywhere 3 to 10 kilowatt. I have a 7 kilowatt system. Jason, 7. What do you have?
Can't remember.
No? Okay, all right.
I don't pay attention to anything when I'm off work. Just like-
Yeah, I assume it's probably in this general range.
3.5 or something.
Okay, yeah, yeah. So pretty average. Yeah, uses inverter-based interfaces. Yeah, when you have smart inverters, they're capable of doing some of this power control. Yeah, so when we think about the broad spectrum of solar that's kind of distributed across all of these rooftops, in the aggregate, the variability is kind of smoothed out, right? But you could actually have pretty steep ramping happening at a local level, right? You imagine like a cloud passes by, right? You can have these pretty big swings, especially when you have places that are pretty dense with solar. And you also have variability at different times. So I just pulled out, so this is actually from my rooftop solar system. Let me try and remember here. Yeah, so this is December 1st of last year. You remember we had some days that were like crazy foggy and cloudy, right? You can see it only produced 9 kilowatt hours on December 1st, and on the very next day, was a sunnier day, literally had twice as much power produced, 18.7 kilowatt hours. And they also provide comparisons of the day before. So even lower on November 30th, only 3 kilowatt hours. So that's a difference in over 2 days of a factor of 6, right? And so there's temporal variability that can be very high. They also give reference numbers for the same date last year, so you can see kind of what that looks like. And then again, pretty big difference temporally by seasons as well, right? So here, this is on June 15th, where I produced 38 kilowatt hours of electricity from my solar panel. So this speaks a little bit to some of that local variability and temporal variability that we see in these systems.
Maybe, 40.3 versus 38 on June day.
Yeah, I mean that's like
How do you account for that?
that's like a 5% variability. I mean that could be like a cloud, right?
Or it could be
Yeah.
wrong.
Yeah. I get all these like spam offers to clean the solar panels, and as I understand, you actually don't need to wash your solar panels very, very often. So, I mean, the rain will do it a lot of the time. So, best not to waste your money, I think.
You have a two-story house?
Huh?
You have a two-story house?
No, it's 1 story.
You could just get them on the roof with a hose.
Yeah, I don't even need to get on the roof. I could just spray it from below. Yeah, and maybe this is something that I've alluded to or we've talked about before, but right, to kind of reinforce net load when we subtract away renewables, because we've had such tremendous growth in solar, both distributed but also utility scale solar in California. You can see progressively the net load curve decreasing more and more over time, right? And so all of this like ramping issues that we think about that's happening over here is getting harder and harder to deal with.
With the ramping issue and having operators change to those resources that can ramp.
Mm-hmm.
Or sorry, maybe taking solar offline early so you can ensure like proper ramping. Have you seen more battery installations so that power isn't just lost?
Yes. In the last 3 years, we've something like tripled the amount of battery storage in California, utility scale. So we went from something, I want to say, like 4 gigawatts up to more than 12 gigawatts. That's, and a lot of folks have attributed that increase in storage to solving a number of issues, including some of the peak power stuff that had happened in like 21, 22. We haven't had to do that since, and a lot of people say that that's because of the additional storage capacity that's been installed. And certainly that's going to help with some of this stuff as well, both to soak in the curtailment when you want to reduce the ramps, but also to just generally help provide extra fast ramping resources during these times. Okay. So just as a refresher, we've talked about net metering from the perspective of the rate design, but physically, I don't think we kind of quite had talked about this yet. So if we think about this kind of setup here as the sort of physical representation of the circuitry, what ends up happening, right, and so your solar power comes in, and and then it generates electricity in DC, which has to go through an inverter. And why is that? Why do we have to go through an inverter?
The grid's an AC.
Yeah, the grid is an AC, right? And so the AC voltage, if you are powering the house, will go through your main utility breaker panel and power to the house. And then, you have some telemetry monitoring systems. You can also export it back through here, and you'll see your arrow kind of going through your utility meter, right? And so if your PV generation locally is greater than the load, then the power flows back onto the feeder, and the meter is going to be net negative. So you are that should be net export, not import, right? Yeah, sorry. These should be switched. Yeah, you're net exporting, so you are selling electricity, and then here you're net importing, so you're purchasing electricity. So if load is greater than PV, some of this is coming in here, but you still require power from the grid. Right, and so with the caveat that we talked about some of these like issues that can happen in backflow where you have voltages going too high. Generally speaking, that stuff is kind of accounted for, but it can be expensive to do so. Yeah, and so behind the meter PV introduces reverse power flow, voltage rise, especially happening on sunny and low load days. That's where you're generating a lot more power, you're using less power, you're gonna have higher likelihood of exporting. And then, as I was mentioning, the smart inverter helps to mitigate these issues. Hosting capacity. So I believe I've talked about these maps before, but PUC requires the investor-owned utilities to release these integrated capacity analysis maps that give DER developers an idea of what the hosting capacity looks like on different feeders throughout their utility territories. And so I took a little snapshot. In Davis, green is where you have generally more hosting capacity, and then yellow, then orange, then red, progressively less and less capacity. And so, it might be a lot easier to obtain like an interconnection request on one of these like green feeder lines as compared to places in red, because if you might be more likely to violate some of the hosting capacity, which could be like your voltage, thermal limits. Okay. Yes.
Does the utility have the power to just like curtail your behind the meter solar?
No. That is like one of the arising difficult constraints that utilities have had to deal with. Ideally, I think they would like to be able to do that, but
It's also one of the benefits to the customer is that like
yeah.
you can always sell.
But there are some limits for the installed capacity that they like to permit.
Okay.
I have ran into the issue that I had to, is you say, oh yeah, I'm getting an EV and I'm gonna have this additional load, so a 7 kilowatt system is justified. I really do want to get an EV. But before that, they were like, you don't have enough time at this residence and enough bills, because I'd only been there a few months, to justify a 7 kilowatt system. So
Yep. So the utility will not allow you to oversize your your solar installation, because you are not only are you mechanically heavily incentivized not to do so under the way NEM works, they also want to minimize just generally the like stress that you're going to be putting out onto the grid. And so with your case, right, until you demonstrate that you are going to use enough load, they're going to be like, oh, this system size that you are interested in is providing more generation than load. You're going to be a net exporter, and we don't want to deal with that.
Yeah. Luckily, I am very good friends with the previous owner, and so I was able to rely on that
Yeah.
person's electricity usage and help my case. But yeah, it can be frustrating.
Yeah. This is maybe a little rehash of what we had discussed before, right? But average residential retail price of electricity has increased even though installation costs have decreased. And this is kind of alluding to this issue with NEM that we have been discussing, right? Everyone else is paying for your solar. If you look at the volumetric charges breakdown, a lot of those fixed costs in transmission and distribution are recovered volumetrically. And so when NEM customers offset their load, they avoid paying for those portions, which include not only generation, but a lot of that fixed infrastructure. That infrastructure needs to get paid for through the customer base, and so that drives everyone else's rates up.
I'll say I recently got a $0 energy bill, my first one, and fixed costs were $62.
Yeah. So,
Just for being connected as like with a rooftop solar system?
welcome to NEM 3.
And that includes gas?
Yeah,
That's
that could.
just the electricity.
Yeah.
Gas, it was up there, but just
So,
the electricity side.
in NEM 3.0, right, you have larger portions that are put onto the fixed cost piece. But I forgot if I had mentioned this, but I investigated my bill more. Apparently I'm NEM 1.0, not NEM 2.0. So I'm even worse. I know. And we have definitely actually had, $0 electricity bills before. The rules for NEM though, there are limits on the sort of export. If you are a net exporter, you don't get like the retail rates. There's a much smaller compensation for being a net exporter overall. And that was actually part of like a legislative bill back in the early 2010s. Yep, and so, yeah, refresher, we've talked about this, right? NEM 1.0, full retail rate, it's, you just kind of pay back based on the rates. NEM 2.0 has non-bypassable charges to help mitigate some of the sort of fixed costs effects getting sucked out in the sort of volumetric charges, right? But generally speaking, the rates are pretty generous still in NEM 2.0. And then NEM 3.0, you get much lower export rates, much stronger incentive for self-consumption. Yeah, some interesting things that have happened. If you look at the growth rate of residential NEM systems under NEM 1 and NEM 2, looks kind of like this. And then very recently, right, in 2022, after NEM 3.0, you can see there's a pretty large sort of drop in solar sales, right? Something like 60 to 80% lower than when it was NEM 2.0.
As part of the design, right?
I don't think they necessarily want to
It's
stop.
yeah, it's not necessarily. I mean, it is an outcome of the design of NEM 3.0, right? But NEM 3.0 isn't trying to get people not to buy solar. It's trying to fix the problem that solar adoption was causing in terms of how it affects everyone's rates.
Okay.
Still remember, there's still this sort of fundamental equity issue that's like, hey, you know, I, as a low income consumer of electricity, have been forced to pay, you know, all of these rates that were put onto me from, you know, the NEM 1.0, NEM 2.0. And now when I can finally afford a solar system, you're saying you're like taking away these benefits, right? And so this is certainly, NEM 3.0 certainly was still a pretty contentious rate structure, even though we see that it solves one of the particular problems that was being caused by
Yeah.
NEM 1 and NEM 2.
Just makes it harder for people to get into solar.
Yeah. Yeah. Okay. So all of our discussion about NEM 1.0, 2.0, and 3.0 have been sort of centered around California, which, to be fair, is kind of at the forefront of you know, DER solar adoption, but not all states you know, do it in the same way. So there are a number of states who are kind of following in the path of California, where you have this full retail NEM. So this is essentially like NEM 1.0, particularly in the northeastern states and some states in the Midwest. Similar to California, they're seeing some of the problems that it causes, and a lot of those programs are winding down and using alternative net energy metering rates. Net billing, so this is where the exports are valued in a different way. So sometimes they do it based on avoided cost or wholesale rates. Buy all, sell all, so this is production that's sold just at a set rate. And then value of solar tariffs. This is kind of an interesting one in Minnesota, where you are credited a rate based on avoided energy, avoided capacity, line losses, and environmental value. And so this tries to think about the sort of consequential value of offsetting electricity production elsewhere with your solar, and valuing that into this particular tariff rate. So a little bit more complicated. Yeah. Yeah, so avoided cost, this is a counterfactual cost to serve marginal kilowatt hours, and it includes the avoided costs of all of these things. Okay, let me see here. Why don't we take a quick 5-minute break, and then we'll kind of wrap up on the solar piece. Yes.
Curious, is the final gonna be weighted toward material after the midterm, cumulative?
Yeah, so it will be cumulative, but it's gonna focus maybe like 60-40, 70-30 on the material after after the midterm. Yeah.
Wow, so net 1.0, that's nice.
Yes.
Happy.
I'm torn between having excellent bills and causing everyone else to suffer.
You can, like, beneficiary guilt, hopefully.
Yeah.
But they expire,
Yes, in like another 10 years or something. I think it's a 20-year contract. And mine started in 2014, so I guess I have another 8 years to go.
right? So if you move out and someone else uses, does that lease renew or?
Well, they stay on the same contract. Yeah, because we took it over in 2020. Yeah. The only time that you would get out of the NEM 1.0 rate is if you make a new interconnection request, aka if you like decided to change the size of your system, you wanted to add another couple panels or something, that would trigger an interconnection request, and then you would get booted off and put onto the newest rate. Yeah. We're actually thinking of upgrading our house from a 1-story to two stories. And one of the things I didn't know about was whether or not that would trigger an interconnection request. But as far as I understand, the answer is no. Like, you just take the panels off and then you put them back on. You're not changing anything about the system. So technically, they don't even need to know that anything changes. Yeah. So.
Are there ways to have parallel systems? You could, like, the new circuits going in for your 2-story, for the 2nd-story room, and you could put those on a different, I guess, probably, yeah.
No, and I mean, 7 kilowatt system is more than big enough for us.
So when you say avoided costs, is that like costs that would have been on the customer or would have been on the utility?
I think of this as like a system cost. I mean, they're going to be distributed in slightly different ways, and who pays for it is, it's going to be, it'll be dependent on a particular sort of category. But the idea is basically like, if I didn't have this solar panel that provided me with electricity, I would need to have gotten that electricity from the grid. And that costs some money to produce. Maybe there's some amount of like capacity costs that's affiliated with producing that electricity. There's a little bit of cost associated with getting that electricity to me. So it's all of the like things. It's the cost of everything to provide that electricity absent my solar panel. Sort of just add it all up. Yeah.
Probably depending on the time of day as well.
Yeah. All of this stuff is tied into that would be part of the energy cost. That would play into your T&D cost depending on congestion. But yes. Don't ask me how they calculate that. I'm sure it's there's some kind of simplified way, but
Probably a spreadsheet.
yeah, counterfactual costs are always kind of hard to prove out in reality.
Yeah, it's like really contentious at the wholesale level,
Yeah.
because there's like
Who knows?
4 or 5 different, like NERC approved,
Yep.
technical performance evaluation methodologies.
Yeah.
So, it's like what you were showing earlier with the load, the peak shaving.
Mhm.
So it calculates that counterfactual, but then it's like, then you have all these companies that are doing like the smart metering or like, and you know, every company has their own kind of like
Yeah.
load factor, so they like kind of nitpick at like the stakeholder meetings,
Yeah.
trying to get their
C-
kind of like,
Because if you think about it, like the idea that you can generate a counterfactual, that all has to come out of some set of assumptions or some set of models, right? And you know, maybe you run a big. I don't think this is how they do it, but you could run like a big system-wide grid model and be like, oh, this is what would have happened, right? But someone can always argue, oh, yeah, like maybe it would have been this thing instead, right? And so, yeah, counterfactual analysis can get pretty contentious.
Yeah.
Okay, so we've mentioned this particular issue. Operators, you know, your utilities typically don't have great telemetry about what happens at the sort of individual rooftop systems. And so they often are taking these sort of forecasting approaches to understand this, right? And so CAISO, for example, wants to have a good grasp, and the utilities, right, also want to have a good grasp of this, you know, at the very least to provide, you know, good forecasts for like their day ahead markets, right? But as we see more and more of these DERs getting installed, you start to have more uncertainty in your forecast outcomes. I think I showed this graph before, right? But this is a real day ahead forecast that CAISO had made. And you can see the actual thing that happened is in black. And their 2 hour, 1 hour, and then RTD, which is the 15-minute, right, all kind of get it not very accurately. And that's because the variation from things like weather and cloud cover is very hard to accurately predict. And when you have a lot of solar resources, you get stuff like this happening. Yeah.
So is that the reason for the load being so variable?
Yes, exactly. Because this is going to be net load. Yeah.
Gotcha.
Yeah. So there's a big push, right, for better data, better telemetry, so that this kind of stuff is better understood. There's like advanced metering infrastructure that helps to get real-time data out to providers. Telemetry from smart inverters that can provide some of that real-time localized data. But yes, this is a traditionally difficult area to kind of deal with, and is getting harder and harder. And actually CAISO and CEC are working together. They recently are developed a program with utilities for better visibility into data and data sharing. Yeah, and they've also had some like recent grant applications to help with forecasting methods.
So what is the proxy PV? Just like a controlled PV installation that you collect data from?
Yeah, it's proxy PV. So one of the things that you can do is instead of getting like slower data sources that provide like localized PV outputs, one of the things that they do is they contract with several companies that provide like real-time PV data streams that are not representing sort of the aggregate capacity, but actually, but enough that you can use that data stream to kind of represent what you think might be happening at a bunch of different local spots. And so, yeah, you're using this like real-time PV information to represent kind of what broadly happens in terms of like PV generation on net load.
Okay.
Yeah. Okay. Interaction with other DERs. So specifically thinking about coupling PV rooftop solar with storage systems. This is something that we see increasingly happen, particularly with NEM 3.0, right? Customers are heavily incentivized to kind of group these things together. This can help smooth exports so that you're actually exporting power back into the grid when on the right times, and also promoting kind of self-consumption, right? So you could store electricity in the battery and then use it and consume it during the evenings. Again, heavily incentivized in NEM 3.0, right? Because your payouts for exports are a lot lower. We can also think about aggregators that use these systems as virtual power plants to provide grid services. And I'll talk a little bit more about VPPs later. But the primary idea is basically like if you allow some aggregator to control your storage and they get to control a bunch of storage devices throughout some region, they can participate in certain markets, right, as essentially what looks like a power plant.
That only works with hybrid systems?
What do you mean by hybrid system?
I guess I've heard Kaiso refer to hybrid as solar plus storage.
Okay, yes. I actually hadn't heard that before, but no. That I mean, I'm. It's not my area, so I'm not saying that that's incorrect. So VPPs don't have to be just from these hybrid systems. There are different ways with which you could form like a VPP. People in my field, right? People have talked about using electric cars as VPPs.
Anything with a battery or capability of storage.
Yeah. So.
Because I imagine if it's just a whole bunch of aggregated like rooftop solar, that might give you some like I don't know purchasing power into the wholesale market, but you can't really dispatch.
Yes. So generally speaking, we do think about dispatchability for VPPs.
All you're doing is load shifting, and it's not necessarily like a VPP, right?
Yeah, that would be more like just demand response types. Yeah. I'm trying to think if there are examples of VPPs that don't include storage. Yeah, I'm not sure. I mean, I guess you could do like a whole bunch of people hooked up with diesel generators, but yeah, they probably wouldn't allow that anyways in California.
What about just demand reduction?
So demand reduction, I don't.
I feel like we have a VPP grant we're working on right now, and
So just on the load.
you're shooting thermostats,
Yeah.
turning up set points or something. I don't know. I mean, we're we're also doing some we have some storage, but I think some of it is like, just like reducing load at strategic times.
Yeah.
But I think that's a broader definition, I don't know.
Yeah, I'm actually not entirely sure. Do you
Not
know
technically pretty-
the sort of?
No.
So we're talking about.
This is like one of the main topics that I was excited to take this class for.
Yeah. So definitionally, right? We think about the flexible load as a sort of demand response resource compared to VPPs, which should be able to have some dispatchability, right? I know that there are some weird exceptions to these types of things, but I'm not so clear on all those details. If you're saying that there are like VPPs that are comprised just of like load flexibility,
You've got slides on it there.
yeah.
It's more like load reduction than load flexibility, maybe both, I don't know. Let me ask, it's with WCEC and they, I don't know, somebody probably knows, I can try to ask.
Yeah.
I wonder what Christy and Caton,
Yeah.
they'd probably tell you like why it's called a VPP, what they're doing. They're the ones who are doing like most of the work.
Yeah, okay. Yeah, I'll talk to Caton about that.
I'm curious what it says.
Yeah, so there's some kind of distinction between VPP and like traditional demand response. I'll have to dig a little bit deeper to get at that. But yeah, so we'll return into VPPs a little bit later. Okay, so yeah, mentioning visually, right, some of this idea about the sort of storage and the kind of services that it has been able to provide. Yeah, so this is data from CAISO that this company Grid Status put together, where we look at the smoothing of gas generation thanks to a lot of the utility scale storage that has been installed over the last couple of years. Yeah, and so you can see what the ramp would look like. So with charging, the 12 to 8 o'clock load ramp is about 5.8 gigawatts, whereas it's almost double that without charging, right? So batteries provide almost like a double service in both load shifting at the same time as being able to reduce the ramping requirements. So I was showing you guys the duck curve shape and how that has traditionally changed out to 2023, but in more recent years, the increase in battery charging has actually shifted us back up a bit and has made the sort of net load ramp problem from the duck curve a little bit easier to manage.
That's a significant difference.
Yeah, well, you know, I always tell students never to do this, but this isn't my plot, right? The axis doesn't start at 0, so it does make that yeah, the scale look a little bit bigger than it should. Yeah, that's a little aside. It's kind of like my pet peeve. I don't know if you guys have ever seen this chart, but it's how does it go? What percent of time axis should start at shouldn't start at 0. So we have and then it goes if you get it, you get it.
Always says
Yeah. But okay, whatever.
It's good to put on a presentation though, I guess.
Yeah, so the battery has helped, but maybe the scale is a little bit deceptive here. Okay. Let's talk about DER and the grid services that you can kind of participate in. So we've talked about, in general, some of the benefits and drawbacks of DERs, and generically the services they provide, but then what mechanisms exist for DERs to actually participate in those services. And so we do have an expert here on this. So if there's anything you want to, feel free to speak up on any of this stuff.
Yeah, you can try.
So there are a number of different sort of pieces of the puzzle when we think about these programs and the ways that people can participate. So there are products that are, or programs that are enabled through CPUC and through the sort of legal authority that FERC provides. There are specific products that CAISO provides. These are like pathways in certain markets. And then actually maybe missing from this, there are sets of programs that utilities have for participation as well. So the first one that I'll mention, there's emergency conservation and behavioral programs. These are non-market-based programs. So anyone who grew up in California in like the 90s and 2000s, maybe I'm like dating myself now, but you guys will probably remember this little icon, Flex Your Power, which kind of evolved into this Flex Alert that is a CAISO program. This is right, so this is non-market, it's not paid, but we still think of this as kind of a load flexibility program. This is a public request for voluntary load reduction during grid stress. So back in the early to mid 2000s, there were tied to things like the Enron scandal, which we'll talk about later. These rolling brownouts and blackouts, and utilities would ask people to kind of voluntarily reduce their load, and so there's this very memorable program, I would say, that if you were around at the time, probably remember.
It's a shame the figure for this, the light switch couldn't have been a thermostat.
Well, back then, turning off your lights probably actually made a pretty big difference because everyone was on incandescents, and so flipping off the light switch actually was a substantial load shed. Yeah.
For the Flex Alert program, do I get something back in return?
No.
Sorry?
Like, do I get something back in return? Like, if you reduce my rate?
You get the thanks of the state. Yeah, this was voluntary. Yeah. There were programs that actually did pay out money. So there's this emergency load reduction program called ELRP, and that pays certain customers for verifiable load drops during emergencies. And it can be actually quite a lot of money, right? So up to something like $2 a kilowatt hour, which is a lot. And then I think this is kind of born out of the sort of Flex Alert program. It's kind of connected in certain ways, but sort of this wireless emergency alert. And so for those of you who were around in 2022 in California, maybe you guys remember this, on September 6th, everyone or most people in California would have received a text that basically said, oh, we're in an emergency situation, we're running out of electric capacity, please conserve power. And so kind of like Flex Your Power, this is voluntary, you don't get paid for it, but people actually did respond to this text in a pretty substantial way. This demand response event happened at around 5 o'clock. You got this text out, and actually the demand dropped by something like 2 gigawatts in the span of 15, 20 minutes. Just from people turning off their ACs, turning off their lights, unplugging their cars that were charging, all that, right? That's a pretty dang good response that you can tap into. But you probably can't do that too many times because people will stop responding, right? And so this really is kind of a last resort emergency type of thing. This is, yeah, I kind of almost think of this as like load shedding, like voluntary load shedding, right? And we always think of load shedding as pretty last resort. Okay, so some of the PUC demand response programs that enable participation. Again, this is, I have a couple of slides just as reference for these programs. We have a base interruptible program, critical peak pricing, smart thermostat DR programs. There is like a program from a third-party demand response called Ohm Connect, which aggregates a bunch of different flexible load resources. There is AutoDR, which is a PUC-funded automated participation program, and this is mainly for larger customer loads, so like commercial and industrial and municipal facilities. And then the SGIP storage, and then the emergency load reduction program that I was just mentioning. Yeah, as another program. So these are programs enabled specifically by PUC, but it's not the only one, right? So we also have pathways to participate in CAISO's market. So proxy demand response, reliability demand response, distributed energy resource provider. Yeah, again, not going to go through all of these specifically, but I'll leave these as kind of reference if folks want to learn more about these programs. Some of these programs are enabled by specific policies. So at the federal level through FERC, and then legislatively, there have been a couple of orders that have helped to facilitate opening of DER markets. And then PUC has released specific regulations and action plans that help enable some of these things as well. So I guess I should probably mention sort of the importance of FERC Order 2222. This was a requirement for system operators to allow DERs in the aggregate to participate in wholesale markets. And that really provides the basis for participation in CAISO and other ISO markets. Any questions about any of this or comments? Yeah, so looking out into the future, this stuff is still developing, and there are some interesting things to think about. So VPPs, in general, are a topic that is still sort of being developed. There are some pilot programs that have tried these sort of VPP structures and trying to see how they work, but still in progress. As I mentioned, for 2222 helps to enable some of these things, and I think in the future, when you see sort of, as we continue to see DER batteries and vehicles, EVs with batteries, I think you're going to see a lot more of this happening. It's just kind of such a large market opportunity. You would kind of imagine that someone's going to step into the market and try and take advantage of those resources. Yeah, and so number of other mechanisms that DERs are going to be able to participate in the future. Yes.
Are DERs in like the early phase? What sort of phase of adoption are we in California for that?
I would say we're not at the really early, like beginning technology stage, but we are, I think, in the early stages of like implementing programs and mechanisms for like broader grid participation. So what that means is like smart thermostats exist, right? EVs are growing. The number of solar rooftops and storage, behind the meter storage, continues to grow. I think that like that, all of that technology, it's not like that's new technology anymore, but it's like penetrating into the broader population more and more.
Yeah.
But what is not so developed is people using all of these resources in coordinated ways to help the grid, right? So I would say over the last decade, we have seen a kind of explosion in utilities and CCAs and even other third-party companies, corporations, who are launching these pilot programs and investigating ways to use all of these technology that people are starting to adopt more and more as resources to participate in the grid, right? And so one of the ways I like to describe it is, for like an electric vehicle, the primary purpose of the battery in the EV is like to move people around, right? To provide that transportation service. But on the other hand, that battery is going to be sitting around for like 22 to 23 hours of the day. And if someone can figure out a way to extract value from that battery, you increase the value of the battery to the consumer, to the aggregator, and the benefit of that is coming from helping the grid in some way. And so likewise with a lot of these other things, it's only a matter of time, I think, before people figure out good, efficient economic ways of capturing that value. Yeah, so going back to this VPP thing, right? So this is sort of an aggregation of DERs, and the idea is that you're operating like a single power plant. I've been kind of alluding to this idea that it has to be dispatchable, but maybe dispatchable in terms of increasing generation or reducing loads, shifting loads, right? That's actually going to look kind of identical on the grid side. And so, however the nuance is in terms of the definition, the idea is the aggregator basically takes DERs and basically makes it look like it's operating like a single power plant, whether we're talking about dispatching generation or dispatching load reduction. So the aggregation is really the key part of the VPP. You're turning these like fragmented DERs into something that's scalable, controllable, and provides a resource to the market. And this is a non-wires alternative, right? And so oftentimes a lot cheaper. It can provide locationally targeted grid support. And so we've talked about the sort of benefits and difficulties of providing that support on the distribution side. And the idea is that certain types of VPPs could help with that. And it also, right, I think this is kind of a often overlooked aspect, but enabling a customer to participate in a grid service without needing all of this technical expertise, right? And so we don't want everyone to have to take a class like this to kind of understand the nuances of like participating in the market, right? The aggregator comes to you and says, here, like install this app or use this particular hardware, hands off, we'll take care of everything, right? And so that's, I think, a cool way of connecting all of this DER services and infrastructure from the customer without having them have to understand like wholesale markets and that sort of thing.
Have you heard of Core Power?
Yes.
It came to the class that Ben and
Yeah.
They have a really interesting product, a smart panel that can control individual circuits in the house.
Yeah. And so I think that really alludes to the fact that you have all these companies that are trying to dig around and find different avenues of value, right? Some of them are going to be successful, some of them won't be, but yeah.
Yeah, I mean, I like it because otherwise, like, you have to replace a lot of devices to be like smart devices. But
Mhm.
at least it's a way that you could have like a dumb house, but a smart panel and
I think that turns it into a smart house, no?
overall.
Yeah.
It's not as granular for control as
Yeah, that's true.
smart devices, but it's
Okay, so we're going to close out talking about economics of distributed energy resources. Right, so capital cost of a particular technology determines our payback. The rates help to shape the way in which we consume and are flexible around providing a particular service. You have export compensation that determines whether or not exporting power is profitable. I mean, this is particularly relevant, right, for the storage and solar equation. Incentives and rebates are an important component to make things affordable and also address equity gaps. And then grid value is the way we determine how utilities value the DERs compared to your wires alternatives. So really, it's this sort of interplay and tug between all of the incentives that the customer has versus what they can extract out of the grid value. So pretty straightforward, right? From a cost-benefit framework, you have some cost of installing some kind of infrastructure. We can divide that by sort of our annual bill savings, and the components of our costs versus benefits are here. And from a market perspective, right, as the payback gets more compelling, I think the more you're going to see people in general go after these things. There is like friction in the system, right, that has to do with the mechanisms with which we can get benefits. Like how hard is it for us to realize these benefits? But as these things get more and more developed, you're going to see those frictions kind of go away, and it's going to be easier and easier to realize a lot of these benefits. Yeah, don't discount the importance of rate design. So we've talked about these different elements, right? But if we think about the way that they interact with DR services, they're gonna be very important in shaping the way that sort of economics and the behavior plays out on the customer side of things. So setting time of use pricing, right, that can be good to have increase the value for self-consumption. So NEM 2.0 and 3.0, fixed charges. This can reduce the marginal value of self-generation, but can help with mitigating the cost shift effect of our NEM programs. Demand charges in certain situations, so we're thinking about large load entities, that can help incentivize things like storage. And then real-time hourly pricing, that helps to align potential operation of DERs in the future with the needs of the system at the sort of wholesale level, yeah.
Isn't reducing the marginal value of self-generation bad as an incentive?
Reducing the value of marginal
I'm
generation.
just trying to digest that sentence.
So having fixed charges reduces the relative value of the like volumetric generation that you're having, right? So that can be
Because you need more generation to make up for the fixed charges?
It's so that your generation doesn't offset the fixed charges that you would want to be paying for certain things. So it is maybe an incentive against solar, but fixes an issue that the solar is causing. This has, right, tying back to the like issues from the NEM 1 and NEM 2 structure. Yeah, I think we already talked about this, so I will move on to future outlook. So net billing export rates. So this ties back into NEM 3.0, which is a sort of transition we've already seen happening in California and starting to happen in other places as well. Electrification in general, so the big ones that we're seeing, right? Shifting energy consumption to electricity on the transportation side, and then away from gas into electricity through heat pumps. This all increases our customer load, but will help improve payback for a lot of these DER systems. And as we think about electrification happening broadly, that helps to actually incentivize some of the DER technologies. A lot more dynamic and locational pricing, which makes DERs, I think, more beneficial as grid assets. So we talked about VPPs through FERC 2222. Yeah, and then generally this idea that non-wires alternatives is going to favor DERs economically in places that are sort of locally challenging. And lastly, we see equity programs growing a lot more to provide incentive for adoption outside of just rich people. Any questions or comments about any of this?
I'm just kind of wondering about, like, with more EVs
Mm-hmm.
and the, like, bad temporal alignment of if you have solar at your home, but your car isn't at home.
Yep.
To be charging off of that solar, like, what do you think is the solution there, like, to those lines? Like, you have the battery, it's just not at home.
Probably local storage.
So storage is one of those, one possible solution. Also, having a lot more workplace charging would help, right? So that would incentivize people to charge at work during the day. Yeah, and so that was like one of the common solutions that have been proposed by some people, is like thinking about charger placement as a way of like shifting the time, is just having access to it. Davis has a fair bit of charging on campus, and I think there's going to be a lot more coming. Is that right? I think we've talked about this before.
Very undefined. The plan is very undefined.
Yeah.
Embarrassingly undefined. So,
Well, let me know if I can help with that.
And then even if I was able to charge my car on campus, I'm not sure I would, because I have to pay for parking.
But actually, for now, since when you park on campus, you pay like a flat fee per day, and if you charge on campus, that flat fee is a little bit higher. But the charging itself right now is free. That's going to change. But the value of the electricity going into your car from that free charging is actually quite a bit higher than the cost to park there. So I think if you are parking on campus for something like more than 3 or 4 hours, it's actually worth it to charge and pay that parking fee. It'll be cheaper than charging at home.
I think
Yeah.
campus is fundamentally unresolved about whether they want to like incentivize people to drive their EVs to work or incentivize them to
You bike and
do something
yeah,
else.
yeah, sure, that's fair.
Or like, and also whether it's their job to provide charging infrastructure. Those are like the two big unresolved questions.
The way that I look at it is, you have the campus has built out all this parking,
Yeah.
right? So I would say the constraint is more about how much parking you have versus those other services. But if the parking's already there, you might as well put the chargers. But anyways, yeah. Yeah, so, I would kind of allude back to the very opening of this lecture when we think about, in general, what DERs are doing to the grid, right? It's a fundamentally different way from the tradition of how we operate the grid, which is these centralized power plants with one-way power flow, and that is now changing in a big way thanks to DERs. And the other thing is, right, we've looked at specific examples of DERs, but in general, right, this is like a very diverse set of technologies that do very different things and can participate in very different ways, right? The ways that solar versus storage versus EVs versus other flexible loads, they will operate differently and contribute to the grid in different ways. Yeah, so there's a bunch of challenges with this stuff, but also, as we've hopefully seen, there's a lot of solutions. Yeah, I'm not gonna rehash all this stuff, but lots of future areas to think about in power systems. I think being involved in DERs probably provides some set of pretty unique expertise and opportunities if you guys are interested in this pathway, right? Whether you're going into utility or CAISO or PUC or CEC, DERs is an area that continues to grow, right? People, the utilities, CAISO, regulatory agencies, other third-party companies continue to expand and hire in this particular area. So, all right. So that rounds out our lecture on DERs. We'll have one more lecture on Thursday. It'll be kind of an interesting perspective at looking at, we're going to look at case study events that have really altered the way that grids have operated and functioned. Next week, our Tuesday lecture is going to be sort of dedicated to review. I don't have any material for that, so I'm going to leave it up to you guys if we want to talk about specific topics and revisit particular things. And then Thursday, we're going to have our final as per our vote. Okay, so I will.
Did you count it correctly?
Yeah, it was pretty. I think it was 7-4. So.
I counted it.
Yeah, we are set to have our final on Thursday of next week. Sorry for those who voted on Monday.